Good day, everyone. Today, I would like to present about the transmission lines and waveguides, which are the foundations of the electromagnetic wave transport. My name is Thangaraj Manimuthu, metric number 2300618 from SIF2013 Electromagnetism 2. Okay, we are diving into the how electromagnetic waves, the same ones that carry your Wi-Fi, radio signal, and satellite communication, are transported. Electromagnetic waves consist of oscillating electric and magnetic fields. They move energy and information through space without requiring a physical medium. To make sure these waves travel efficiently, waveguides. These are engineered paths that control the propagation of these waves, especially in high-speed systems. So, the next, what are transmission lines? So, what exactly is transmission lines? Transmission lines are conductive structures that carry time varying voltages and currents. They transport energy from one point to another, often supporting the DEM mode, where both the electric and magnetic fields are perpendicular to the direction of travel. Some common types include coaxial cables, like the one connecting your TV or internet routers, twisted pairs, which are found in Ethernet cables and telephone lines, and also the final one, microstrips, used on the circuit board for high speed signals. So let's talk about the next, which is telegrapher's equation. So to analyze the transmission lines, we use the telegrapher's equation, which are derived from Maxwell's equations. So these equations, which I provided below, describes how voltage and current behave along the line. These equations help us to understand things like signal delay, distortion, and reflection for the key consideration in the design of communication systems. So let's go to the next, which is characteristic impedance and matching. So one critical concept of transmission lines is characterizing impedance, denoted as Z0. This is the impedance of the line, which is defined as I have shown in below. Matching the impedance of the source, transmission lines and loaded is vital to avoid signal reflection. If the impedance doesn't match, part of resulting in power loss and distortion. Perfect impedance matching means no reflection and maximum power transfer. So the next is real world application of transmission lines. So transmission lines are everywhere. Coaxial cables connect your TV or routers to the other side world. Twisted pair lines from the backbone of telecommunication and Ethernet networks. Microstrips are used on PCBs to transport high frequency signals. So, in this, they are crucial in high speed digital design, including 5G networks, Wi Fi systems, and even in your LOT devices. So let's go to the next, which is introduction to waveguides. Now let's talk about the waveguides. Unlike transmission lines, waveguides are hollow metallic structures used to carry electromagnetic waves, usually at high frequencies. They guide the waves by reflecting them off the walls, and they typically operate above 3 gigahertz. At higher frequencies, transmission lines become inefficient due to energy loss, which is where the waveguides shine. So the next is waveguides support different modes of wave propagation. So the two main types are transverse electric, where the electric field has no component in the direction of the propagation actually, and also the transverse magnetic, where the magnetic field has no component in the direction of propagation. So each waveguide has a cutoff frequency, so below the frequency, so that the wave cannot propagate. For example, for a rectangular waveguide, the cutoff frequency is calculated using the formula which I've given below. So the next is advanced model and field patterns. At higher frequencies, waveguides can support more complex modes like TE20 or TM11. These modes have multiple lobes or nodes, and they are used for more specialized applications such as high bandwidth communications or specific antenna patterns. However, these higher order modes can cause issues like dispersion, where different parts of the signal travel at different speeds, leading to signal distortion. So, the next is let's go to the real world application of waveguides. Waveguides are used in systems that require high frequency signal, such as satellite communication, where transmitting data between Earth and satellites, radar systems, which are using microwaves for navigation and detection, medical imaging, so that the waveguides help transmitting high frequency signal in MRI machines, and industrial heating, for example, in microwave ovens. So, the next is the comparison of transmission lines versus the waveguides. Let's quickly compare transmission lines and waveguides. I'm not gonna go through everything. Transmission lines works well for frequencies up to 3 gigahertz, are compact and flexible, but they have higher loss at high frequencies. By the way, for waveguides, excel at higher frequencies above 3 gigahertz, are more efficient but are bulky and less flexible actually. So the choice depends on the frequency and the application of the devices. So finally, we are in the conclusion. Both transmission lines and waveguides play essential roles in modern communication systems, radar, and medical devices. Transmission lines are perfect for low to medium frequencies, while waveguides are handled to high frequency applications. Understanding both help us to design more efficient systems that connect our digital world from Wi Fi to space communication. That's all. Thank you.